The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture to be or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I will respond as soon as I can. All right, so eventually today we're going to get into 11.5, but first we've got a couple of questions from 11.4. So this is 11.4 number 9, and let's look at it on WebAssign. It says fill in the blank, part A, fill in the blank. And it's a little confusing looking at it there, but part A, so we've got log of x equals log, and then I believe that there's supposed to be a box down below and then x. And so let me show you that again on my whiteboard. So what they're trying to get you to see or to declare is that if there's no base written, that's an implied base 10. So that log, log of something, is log base 10 of something. That's part A. Part B, it says log base 5 of 5 to the x power equals something. Okay? Now, if we take this equation and change it to an exponential equation, we'd have 5 to the box equals 5 to the x, which means the box would be x. So part B, the answer would be x. Any questions about that problem? Okay, we're going to look at another student's problems here. There we go. This is also from 11.4. And this is also starting with number 9. Let's see here. So the first part A, is pretty much the same thing as before. They want us to show that log x equals log base 10 of x. Part B, we have log base 8 of 8 to the x equals what? Okay, so again, part A, the missing piece is that it's log base 10. Part B, log base 8 of 8 to the x equals some unknown box. Changing that to an exponential equation, we get that, which means the answer is x. Any questions on that one? All right, then we're also going to look at number 49. So this is 11.4, number 49. And okay. So we've got this huge formula here. Okay. So I'm going to recopy that. N equals, in the numerator, it's the log of AR over P plus 1. And in the denominator, the log of the quantity 1 plus R. Let's see. P is the $1,000. So P equals $1,000. R is 7%. 7% or 0.07. T, or excuse me, hang on here. That's not what I wanted to do. Here we go. Okay. Let's see. N is the number of years. That's the unknown. And $A is the amount that's in the account at the end. That's the $15,000. So let's see, we've got P, A, R. So we've got everything except N, which is what we're trying to find. We're supposed to round to 1 decimal place. Okay. So substituting all of these numbers into this formula, we get n equals the log of A, which is 15,000, times R, which is 0.07, all over P, which is 1,000, plus 1. And on the bottom, the log of 1 plus 0.07. Okay, so I'm going to take what's inside the brackets on top and simplify that. So I've got 15,000 times 0.07 divided by 1,000, and I get 1.05 plus 1. So on top, I've got the log of 2.05, and on the bottom, the log of 1.07. So let's see, if we take the log base 10, not log base E, of 2.05, close it up, divided by the log of 1.07, close that up, and I get 10.6097, etc. It said to round to the nearest, to one decimal place, so n would be 10.6 years. Any questions about that problem? Okay, well, those were the ones that people requested. Do you folks have any questions before we go on?
Yes, number 7, please.
Number 7?
Yes, 11.4.
Okay, hang on. Let's find yours. Let's see. Here must be in 4781. And you said which section?
11.4.
11.4.
Number 7.
Number 7. Okay. All right. So complete the table of values. It says f of x equals log base 7 of x. And then we have when x is 49 and when x is 1 over 49. Okay. So now, let's go back here. Okay, so if x is 49, f of 49 would be log base 7 of 49, right?
Okay.
But what is that? Well, log base 7 of 49, let's just call it some unknown box, okay, for now. But now we've got an equation. We could rewrite this logarithmic equation as an exponential equation, which would be 7 to the box power equals 49. Are you okay with how I got there?
Yes.
But I could take 49 and write it as 7 squared. So if 7 to the box power equals 7 squared, the box equals 2.
Okay.
You all right with that?
Yes.
Now let's take a look at the second one. And what I'm going to do here, I'm going to just erase all this so that I don't have to recopy the other stuff. Of course, it's going to take 3 hours to erase this with this sad pen here. Okay. Good enough. So f of 149th would be log base 7 of 149th. Okay. But log base 7 of 149th equals some unknown box. Changing it to exponential form, 7 to the box equals 149th. Okay with that?
Yes.
All right. So now 7 to the box equals 1 over 7 squared. 7 to the box equals 7 to the negative 2 power. So the box equals negative 2.
Okay.
All righty. Anything else?
Yes. No.
Okay. Well, then let's go on to today's lesson, which is section 11.5. We talked about base 10, log base 10, common log. Log base 10 is used considerably in mathematics. There's another base that is used quite a bit, and that is base, the number e. Now, e is kind of like pi. Pi is approximately 3.14159, and it just goes on, okay? It's an irrational number. It doesn't repeat, it doesn't stop, it just goes on and on. E is approximately 2.7, let's see, 1828, I believe it is, yes. Now, we use E when we're dealing with situations where we've got what's called exponential growth or exponential decay. If we have a population of something and it's either growing or decaying continuously, we tend to use this number in the formula, okay? And the formula that we're going to be looking at is this. It says A equals PE to the RT power, okay? That's a formula where we're dealing with continuous growth or decay. Now, let's take the population of Yakima. Is this the way things work? From January 1st to December 30th, no one dies, no one's born. Suddenly on December 31st, you open the paper and there's all these people that died and there's all these people that are born. No, every day there's things in the paper about people dying, people being born. It's a continuous process. So let's, if the Yakima is growing, let's say at a rate of 1% per year or something, we think of that as a continuous rate, not just all at the end of the year kind of thing. So again, that kind of a situation, we would use the number E. And we'll talk more about that in a little bit. Log base E is commonly used. And so again, they have a shortcut notation, but they've already used plain old log. So they call log base E natural log, and they write it as ln. Why isn't it NL for natural log? I don't know, but anyway. So ln means log base E, just like log means log base 10. So that's some notation you need to get used to. All right. What I want to do now is I want to look at some, well, a graph in particular. And so give me a minute here. We'll switch over to the graphing screen. And let's see here. Let's go right there. Okay. So in a previous class, we looked at something like y equals 2 to the x and y equals 3 to the x. Well, if E is approximately 2.7, then y equals e to the x should lie between that one and that one on the graph. Okay, what I'm going to do now is just find some table values for y equals e to the x, and then we'll plot the graph. And again, I'm going to use -3 to +3. Those aren't always the best choices, but when we've got a exponential equation, the form y equals b to the x, in this case, b is e, 2.7-ish, these are good values to use. Now, on your scientific calculator, you may not have a button that just says E right up on top. But if you look over on the left side, the left column, there's a button that says LOG. We talked about that yesterday, I think, or the day before. And the second function key is 10 to the x. Right below that, there's a button that says LN, and its second function key should be e to the x. So I want e to the negative 3 power. So I'm going to go second e to the x, which brings up this. I'll put in negative 3 and close the parentheses. And I get 0.0497, et cetera, et cetera. I'm going to go ahead and round that to the nearest hundredth, so make it 0.05. Okay, I'm not going to be able to graph it that accurately, excuse me, on this graph anyway, but you'll get a general idea. So now I'm going to go back, and instead of negative 3 as an exponent, I'm going to use e to the negative 2 power, which is approximately 0.135. So I'm going to round that up and make that 0.14. Okay. Let's see. E to the negative 1 power is approximately 0.367. So we'll say 0.37. E to the 0 power is 1. E to the 1 power would be 2.7-ish. And I know I was rounding to the nearest hundredth, and now I've gone to the 10th and whatever. And again, I'm not too concerned about accuracy, super accurate, because I'm not going to be able to graph it that accurately. Okay, so let's see. E squared is 7.389, so we'll say 7.39, and E cubed is 20.085. So again, I know I'm not being super consistent in my rounding, but it'll still give me a rough picture. Okay, rough is right. All right, so when x is negative 3, y is 0.05, which is right down close to the x-axis. At negative 2, we go to 0.14, which is about 1/7. That's just slightly above it. At negative 1, we're at 0.37, which is about 1/3. 0, 1, I'm feeling good about that point. 1, 2.72, 7.39, and 3, it's off the graph. So what do I have here? Let's see if I can find a piece of my plastic graph here that makes it accurate. I see we lost you there. Are you back?
I'm back.
Okay. Let me okay. Can you see my graph now?
Yes.
Okay. So there's y equals e to the x. Very much like 2 to the x or 3 to the x. Again, it's hard to think of e as a number. It looks like a variable, but it is a number. All right. So now let's go back to my other screen. And okay. Now, I talked a little bit ago about this formula. And we use this formula when there is continuous growth or continuous decay. It says, find A using the formula A equals P e to the RT, given the following values of P, T, and R. Round to the nearest hundredth. Okay, we are told that P equals 5,000, R equals 8%, which we again convert to a decimal, 0.08, and T equals 20 years. So A equals P times E to the 0.08 times, oops, not times 8, times 20, times 20. Okay, so on my calculator, let's see, I've got 5,000. Second ln button. So I get second, I get e to the x. And then in my exponent, I put 0.08 times 20, close that up, and I'm getting 24765.16212. And it said to the nearest hundredth, which would be there, the 2 would round down. So I get 247, oops, wrong place for the comma. Sorry about that. 24,765.16. Any questions about that situation? So I'm just plugging numbers into the formula.
No.
Let's take a look at another one. So we use again A equals P times e to the RT. Now we have P equals 15,895. R equals -2%, which would be -0.02, and T equals 16 years. So A equals 15,895 times e to the -0.02 times 16. And let's see what we get there. 15,895 times e to the -0.02 times 16, close it up, 11542.13894. So rounding to the hundredth, the 8 would round up, so we get 11,542.14. We okay with that? I'll take that as a yes. Okay, now it says evaluate each expression without using a calculator. The natural log of e to the 5th power. Now recall that the natural log is the same thing as log base e. So what we have is log base e of e to the 5th power. Okay. The base of the log is e, and the base of the exponential expression is also e. So this is equal to something. Taking this logarithmic equation and changing it into an exponential equation, we get e to the box equals e to the 5th power. So the box equals 5. So the natural log of e to the 5th is 5. Any questions about that?
No.
Okay. The natural log of e to the 4th, what do you think that would be equal to?
Four.
Yep. Because this would be log base e of e to the 4th equals box. E to the box equals e to the 4th. The box equals 4. So if the base here is the same as the base there, it's like they somehow undo each other, don't they? And that exponent remains. Yeah. It's not really magic, but we're not going to get into that right now. Okay. Natural log of 1 over e cubed. That would be log base e of 1 over e cubed, which would be equal to some unknown. So e to the box equals 1 over e cubed. But 1 over e cubed would be e to the -3 power. So here's a case again where we're doing something that we didn't used to do. Instead of taking a negative exponent and rewriting it so it's positive, we're actually taking a positive exponent and rewriting it so that it's negative, because we need this form. So now the box is -3. All righty. Let's take a look at some calculator problems. Let's find the natural log of 0.675. So now I don't push the second function key, I just push the key that says ln, and I get this. Then I put in 0.675 and close it up. And I get -0.3930425881, but it says to round to 4 decimal places, which would be there, The 4 in the fifth place would round down. So it's going to be approximately negative 0.3930. Okay. How about the natural log of 2.7? The natural log of 2.7, and I'm getting 0.99325. The 5 will round up, so 0.9933. Okay. Any questions there?
No.
How about the natural log of negative 10? Oh, I get an error message that says non-real answer, quit. Your calculator might say domain error. And why is that? Well, I think we talked about this the other day, but let's refresh the idea. If we have y equals b to the x, the base has to be greater than 0, and it can't equal 1. X could be any real number, and y has to be greater than 0. Okay, so when an exponential equation is written in that form, a basic form, the base has to be positive, not equal to 1. The exponent can be positive or negative or 0. The final answer over here has to be greater than 0. Well, if we take that and we change it into a logarithmic equation, we get log base b of y equals x. This is the same y that was, so it has the same restrictions, which means that that quantity we take the log of has to be positive. So we can't take the log or the natural log of a negative number, which is why when I did this, it gave me it's a domain error kind of thing. All right. Okay, now I want to compare two formulas that we've had. One of them is this. And the other one is this. The first one, we had that for compound interest earlier on in this chapter. That's when the compoundings occur yearly, semi-annually, quarterly, monthly, daily, etc. But if they occur continuously, that's when we would use that second formula. Okay. So this is used when we're talking about continuous growth or decay. This is used when we're talking about compoundings that are not continuous. All right. This next problem, the directions right from the start, it says continuous compound interest. So we're going to be using this formula, not that one. An initial investment of $2,000, so that's P, earns 8% interest, so that's R. Compounded continuously, that's why we're using this formula. What will the investment be worth in 15 years? So we know P, R, T, we just need A. So A equals $2,000 times E raised to the 0.08 times 15 power. So $2,000, and then I've got e to the 0.08 times 15. I close that up, and I get 6640.2338, etc., etc. This is money. We're going to round to the nearest cent. $6,640.23. All right. Are we okay with that? Any questions there? Let's take a look at another situation. This says determining the previous balance. An account now contains $3,610 and has been accumulating interest at 8% annual interest compounded continuously. So there's the clue. I'm going to use that. Okay. They don't tell us the beginning amount, they tell us the ending amount. It now contains $3,610 and has been accumulating interest at a rate of 8%, compounded continuously. How much was in the account 4 years ago? So we're working backwards. It's like Jeopardy. We know the answer. What's the question? The answer is $3,610. The question is, how much was put in at the beginning? Okay. So we get $3,610 equals PE to the 0.08 times 4. Because I'm going to isolate P, I'm going to predetermine what 0.08 times 4 is, which is 0.32. Now to isolate P, I'm going to divide both sides by e to the 0.32 power. So P equals $3,610 divided by e to the 0.32 power. Okay, so 3610 divided by e to the 0.32 power, and I get 2,621.398. That's going to round up $2,621.40 to the nearest penny. But again, be careful, read that very carefully. It's telling you the end value, asking you the beginning value. Okay. Here's another problem. It says bed bugs. How fun is this? If not checked, the population of a colony of bed bugs will grow exponentially at a rate of 65% per week. If a colony currently has 50 bed bugs, how many will there be in 6 weeks? Okay, so we're talking about exponential growth or decay. So we're going to use A equals PE to the RT. It says it's growing at a rate, so R is 65% or 0.65, and that's per week. The colony currently has 50 bed bugs. How many will there be in 6 weeks? Okay, so we know the starting amount, we know the growth rate, we know the time. Let's find the final population. A equals 50 times E to the 0.65 times 6 power. And so let's see actually how I wanted to write that. Let's write that again here. We'll say to the parentheses 0.65 times 6. Okay. So 50 times e to the 0.65 times 6 power. And we get about, can't spell, about 2,470, because it comes out this and you don't have a partial bed bug, so about 2,470. I guess a partial bed bug would be a good thing, because then it would be a dead bed bug. Any questions on that one?
No.
Okay. This one says the Big Easy. I think that's a reference to New Orleans. I'm not sure, but it says New Orleans has steadily won back some of the population it lost in the wake of Hurricane Katrina in 2005. If the current 8.2% annual increase in population remains constant, How long will it take for its population to double? Okay, so we're talking about a population that's growing. So we're going to use A equals PE to the RT. The current 8.2% annual rate. So R is 8.2%, which is 0.082. How long will it take? So time is the unknown for the population to double. So it doesn't give us the initial population and it doesn't give us the ending population. What it says is whatever population that is in 2005, how long will it take to double? So if we just call the population at the beginning P, the ending population A would be double that, or 2P. Okay? We still don't know what the population is, but the ending population is twice the beginning population. So now plugging the information into the equation, we get 2P equals PE to the 0.082 T power. Okay? We all right with that?
Yes.
So now I'm going to divide both sides by P. And we get 2 equals E raised to the 0.082 T power. So it didn't really matter that we didn't know the population because we've now divided P out of both sides of the equation. I'm trying to solve for T, but T is part of the exponent. So I'm going to change this exponential equation into a logarithmic equation, which would be log base E of 2 equals 0.082 T. But isn't log base E just natural log? So I could write this as ln natural log of 2 equals 0.082 T. Then we'll divide both sides by 0.082. And T equals the natural log of 2 over 0.082, which is, let's see, the natural log of 2 divided by 0.082. Hang on here. Yeah. Is 8.4530, etc. And let's see, they rounded to the nearest tenth, so that would round up, we'll say about 8.5 years. Yeah. About 8.5 years. Any questions on that one?
No.
Let's take a look at this right here. Where did the 0.082 come from? Where did that number come from?
The R.
R,
percent.
right? Now, consider this. I could have put any number I wanted in there for P, right? Because if I'd have 2P on one side and P on the other, I divide both sides by P and I'd have 2 equals that, right? So whether P was 1,000 or 1,000,000 or 42, once I divided it out, I would have had this equation, which would have led all the way down here. But we established a minute ago that this bottom number was R. So in fact, T equals a natural log of 2 over R is a formula for when you want to double something. Because you're starting out with some population here at the beginning and doubling that population at the end, going through the process, you're going to arrive down here. So we could have just gone straight there and put 0.082 in and gotten our answer. Okay, so there's a doubling formula. Now, let's apply that on this next problem. It says doubling money. How long will it take $1,000 to double if the interest, if it is invested at an annual rate of 5% compounded continuously? There's the clue. If it hadn't said compounded continuously, if it had said quarterly or monthly or whatever, then we couldn't use this formula. But so we've got this situation, but we're going to double the money. So how long is it going to take to double it? Well, the time would be the natural log of 2 divided by r. And r in this case was 5%, which would be 0.05. So we have the natural, whoops, turn the calculator back on, the natural log of 2 divided by 0.05, and we get 13.86, and that rounds, if we round to the nearest tenth, that would be approximately 13.9 years. So $1,000 doubles at 5% continuously, it takes 13.9 years. Again, I don't need the amount of money in there because it's going to start out as 1,000 and end up as 2,000, and then you're going to divide both sides by 1,000, and you're going to have 2 equals e to the RT kind of thing. Okay. So new information. Log base e is natural log. A equals P e to the RT, continuous growth, and T equals natural log of 2 over R, doubling formula. All righty, tomorrow, which is Wednesday, we wrap up the chapter. Today, we're just going to do 11.5 for homework. Tomorrow, we're going to wrap up the chapter. Thursday, we'll have a review, Friday, the test, and then Monday, we'll review for the final on Tuesday of next week. There's your whole life in front of you for the next week. Anyway, have a great rest of the day. I will be back at 1:15